Hi everyone, welcome back to Dave's Math channel. I'm your host David Tear. Last video I made I misspoke. I said it was going to be the last video on derivatives. Actually I have two more to do, including the one I'm going to do today. Today I'm going to talk about the most general form of the power rule, which works for arbitrary real exponents, and it's written down here. It's really the same rule we've seen already. I'm just using alpha instead of n for the exponent. So the derivative of x to the alpha is alpha times x to the alpha minus 1, where alpha is now an arbitrary real number. Could be positive, could be negative, could be a fraction, could even be an irrational number. So how do we prove this? Well, it's actually pretty simple given what we know already. So here's what we do. We're letting f of x be x to the alpha, where alpha is an arbitrary real number now. And what we want to first do is rewrite f of x. And we can do that by first writing x as e to the log x, because we know that's an identity. X is equal to e to the log x, whatever x is. And we can now raise that whole thing to the power alpha. And that's going to be f of x, and we can rewrite this thing as e to the x log alpha. So that's just another way of writing f of x. F of x is x to the alpha, but we can also write it as e to the alpha log x. And now we can apply the chain rule. So we can write f of x as g of h of x, where g of x is now e to the x, and h of x is alpha log x. So let's do that. So now we know what the chain rule says. The derivative of f of x, f prime of x, is equal to g prime of h of x times h prime of x. Well, g prime of x is e to the x, g of x is e to the x, so g prime of x is e to the x. I think I rewrote these wrong. But so g prime of h of x is e to the alpha log x, which is really just x to the alpha, and h prime of x is alpha over x, because the derivative of natural log is 1 over x. So now we just simplify this expression. Note that the thing on the left, e to the alpha log x, is really just x to the alpha, and we're multiplying that by alpha over x. And so when we're done, we get alpha times x to the alpha minus 1. That's the proof. So that's how you prove the most general version of the power. Pretty nice result. Here's some important examples here. So special cases of these involve nth roots. The one you probably see the most is derivative of square root. You'll see this a lot. Derivative of square root of x. And I think this one's even worth memorizing because you see it so often. But, just applying this rule, just remember the square root of x is x to the 1/2 power. So we can apply the power rule to that. We get 1/2 times x to the minus 1/2. Well, we can rewrite that as 1 over 2 times the square root of x. And like I said, you'll see this a lot. So I think that's a good formula to memorize. The other ones you probably don't have to memorize. They're probably easier to derive. So you can do this for arbitrary roots, not just square roots. So for instance, derivative of cube root, if you work this out, is going to be 1 over 3 times the cube root of x squared. Or more generally, the derivative of the nth root of x turns out to be 1 over n times the nth root of x to the n minus 1. But you won't see this very often. If you do, it's probably easier just to derive it. But I would recommend memorizing the form for the square root because you do see that one a lot. But it's not hard to derive anyway. So anyway, that concludes my video. I'm done with the power rule now for arbitrary real exponents. And I have one more video to make on derivatives. That's going to be derivatives of inverse trig functions. And those are going to be pretty easy just using the inverse rule I derived last time. So anyway, that concludes my video. Long live math, and I'll see you guys next time. Bye.